Okay, so now let's take a look at how we solve these two additional discussion problems. This first problem, so you have a uniform rod of mass M and length L from point A to point B. Okay, it is supported at point A. It can rotate frictionlessly in a vertical plane around point A. Now, if there's nothing else attached to it, it's just a physical pendulum. And we have already learned how to find the period of the simple pendulum and physical pendulum. The difference here is that we have the additional spring attached to the lower end, point B, of this rod, and the spring is massless and horizontal, okay? And it is set such that when the rod is vertical, which means the line connecting A and B is vertical, the spring is at its natural length, so it doesn't exert any force on the rod. Now, as we pull point B of the rod to the left or to the right, then we'll either be elongating or compressing the spring. So the spring will give you a restoring force on top of the gravitational force that's already exerted on the rod. And let's see what happens if you pull point B to the left, and therefore making the spring longer. And the spring will give you a force pulling the rod back towards the right, and that force is K times X, right? X is the amount of stretch of the rod, so it's the distance between the origin point here and point B. Okay, so that distance between here and there, that is X. And so there's a restoring force, Kx, exerted by the spring on the rod. And that alone will allow the rod to oscillate back and forth. But on top of that, there is also a gravitational force. And gravity also provides a restoring force in the sense that it creates a torque that is clockwise as the rod swings counterclockwise. Now, we can use two general methods to solve problems like this to make sure that there is a simple harmonic motion, and we even find the period of the simple harmonic motion. But let's focus on the first method, which is force/torque. I mean, the second method is energy. We can do that as well. You look at the force and torque method. When do you use force and when do you use torque? Well, generally speaking, when there's rotation involved, torque is a better method, and sometimes the force method doesn't work, because when it comes to rotation, there is a pivot point, and there's an external force exerted at the pivot point to keep the rod from moving at that point. Okay, so in this case, it's point A. There is an external force at point A provided by the ceiling, and that we don't know what that force is. And therefore, if you want to use F equals ma, you wouldn't know what that force is, so it's not a good idea to do that. On the other hand, if you use a torque approach, the rod is rotating about point A, and therefore, if you use point A as a reference point to calculate the torque, you find that whatever force exerted at point A will produce no torque at that point, and therefore, we don't have to worry about the torque provided by that force because it's zero, the lever arm being zero. Now, there are two forces that do provide a torque. One is gravity. As you know, gravity causes a counterclockwise torque about point A. And the other is the force of the spring Kx that also provides a counterclockwise torque. So both provide counterclockwise torque as theta increases. And if we choose the increasing direction of theta as positive, that's a clockwise direction. Both of these torques are counterclockwise, so both of these torques are negative. Okay, and we can add these two torques up to find a net torque, and that should be equal to I times alpha. I should be calculated about point A, right? We just apply the torque theorem. Okay, so let's do that. Right, let's take the torque approach. So apply. Torque equals I alpha. Everything is about point A. Okay, I need to apply torque theorem about point A, then I don't have to worry about any torque of a force going through point A. Okay, the torque from point A, there are two terms. One is from mg, the other is from kx. Now, as you know, torque is equal to what? Force times lever arm. So here's a force, right? Here's a force. And here's a point of interest, in this case, point A. You draw a line perpendicular to the line of action going through point A, and that is the lever arm upward. So torque A equals F times upward. Okay, positive meaning it's clockwise, and negative meaning it's counterclockwise. Now in this case, look at the force the torque provided by mg. Okay, using this knowledge. Okay, so let's do that. I'm going to draw a line of action of the force of mg. That's the line of action. Okay, so starting from point A, I'm going to draw a line perpendicular to the line of action from here to there until I reach the line of action. So this distance is the lever arm, right? This distance, I'm going to use a different color for that distance. I'm going to use a purple color. That purple distance, that is the line of that is the lever arm of the torque provided by mg at point A. And we know what that force is. We know that torque is now. The lever arm is half of L times sine theta, right? Because this angle is also theta. This angle is also theta, and the distance between here and there is just half of L. Okay, so the lever arm of mg is half of L sine theta, and then times mg itself. That gives us the magnitude of the torque. It's negative because it's counterclockwise. Okay, similarly, we can calculate the torque provided by kx, and we need to find the lever arm again. So again, we start from point A, right? We draw a line that's perpendicular to the line of action, which is this, which runs through the spring. And so this lever arm is just L cosine theta, right? L cosine theta. And the force is kx. So, and it's negative. The torque is also negative because it's also counterclockwise. So therefore, it's force kx times L cosine theta. Okay, that's the torque. And that equals IA times alpha. Okay, now let's clean things up a little bit. I'm assuming that the angle theta is very small because x is very small compared with L. Okay, so therefore, since the absolute value of theta is far less than 1, as the absolute value of x is far less than L, we have sine theta is roughly equal to theta, or tangent theta, however you look at it. They're almost the same, and therefore I can relate x and theta, because tangent theta would be sine theta would be x over L, right? Sine theta is x over L. Okay, and x is roughly equal to theta. Sine theta is roughly equal to theta, so therefore I have x is roughly equal to L times theta. Okay, so that's how we relate x with theta. So we don't have two variables anymore, x and theta. I just want one variable, either x or theta. So let's keep theta as a variable, because in alpha is just a second derivative of theta with respect to time. So I'm going to keep theta as a variable. Okay, so let's clean things up. And the first term now becomes negative mg over L. Negative mg L over 2. Sine theta is roughly theta. And the next term is kx. Now remember, x is about the same as L times theta. Okay, replace x with L times theta, you get KL theta times another L cosine theta. So it's KL squared theta, right, times cosine theta. Now cosine theta is almost equal to 1 because theta is very small. Okay, so ignore cosine theta. You just replace it by 1. Okay, and that equals what? IA times alpha. What is IA equal to? Well, you recall from physics 8A that for a rod, you calculate the rotation inertia about one end of the rod of mass m and length L. It's 1/3 ml squared. 1/3 ml squared. Okay, times alpha. Alpha is the second derivative of theta with respect to time. Okay, now is this simple harmonic? Well, what's the signature of a simple harmonic motion? What kind of equation of motion do we get? Well, the equation of motion of a simple harmonic oscillation is that the restoring force or restoring torque is linearly proportional to the displacement, either x or theta. And is this the case? Yes, it is, because if you take that theta out, and combine these two terms, you will get a constant times theta with a negative sign coming out. Okay, so let me rewrite this as 1/3 ml squared times the second derivative of theta with respect to time, and that equals to negative, I'm just taking the constants out, mgl over 2 plus kl squared, and then theta. Okay, now if you compare this with the standard mass and spring equation of m a equals to negative kx, remember that? Here a is the second derivative of x, just like here you have the second derivative of theta. And then we know that this leads to a simple harmonic oscillation, right? This leads to a simple harmonic oscillation, and that I can find that as x equals a cosine of omega t plus phi initial with omega as the square root of k over m. Okay, now in our case, we don't just have kx, we have also, we have a spring attached and gravity as well. So still, if we compare these two, you can think of this, you can think of this whole thing as analogous to the constant k in front of the variable theta instead of variable x. And this whole thing I can think of effectively as the mass in front of the second derivative. Okay, so think of this as m effective, and think of this as k effective. Okay, so I have myself a simple harmonic oscillation. I have theta equals amplitude of the angle and then cosine omega t plus phi initial, where omega equals the square root of k effective over m effective. Okay, and do I know what k effective is? Yeah, k effective is just this constant mg L over 2 plus k L squared. Then I have to divide this by m effective, which is 1/3 ml squared. Okay, once you know that, you can find t. So t is equal to 2 pi over omega, and you can work that out. So indeed, this is a simple harmonic oscillation. Okay, so what we did was we combined the torque provided by gravity and by the spring force, and applied the torque theorem and use the simple harmonic approximation, which is valid for small angle of oscillation theta. Also, we have to replace x in terms of theta because I don't want two variables here, x and theta. I chose to keep theta, again, because I have a alpha here, which is second derivative of theta. So I don't want to use x, I use theta as the variable here. Okay, so that's how we do the first problem. You can also redo this problem from energy approach. The way you do that is by adding the total energy of the system, which includes 3 types. One is rotational kinetic energy. The second one is the potential energy of the spring, and the third is the potential energy of gravity. You add these three terms up, and you want to, of course, the sum is a constant because all the forces doing work is conservative here. So therefore, you have conservation of energy. And when you did that, you can, after you do that, and using the same approximation of small angle, you can then compare the standard result with the standard result of, for any simple harmonic system, the energy E has to equal to, for standard mass and energy system, the mass of spring system, 1/2 m v squared plus 1/2 kx squared. And you're gonna get m effective and k effective. Okay, x is replaced by theta in this case, and v would be d theta dt in this case. So you can compare with that standard expression, you can find what k effective is, what m effective is. And hopefully, if you did that, you'll get the same exact k effective and m effective as we saw here. So please give this a try, okay? And if you run into issues, please let me know. So that was the first problem. Now the second problem is a little bit different. Here we have a case with 2 masses, one sitting on top of another. there is friction between these two masses, but everything else is friction-free. Now, the lower mass, 1, is attached to a massless spring and can move frictionlessly on the horizontal table. So imagine I pull this lower mass this way, okay? Pull it by a certain distance, and then by this, which I call A. Then I let go of it, it starts a simple harmonic oscillation. Now, imagine if A is pretty small, okay? Then both blocks will be moving together, back and forth, powered by the spring. And if the amplitude is pretty small, then clearly both blocks are moving slowly with little acceleration, and there's enough friction to hold this top block so that it doesn't slide against the lower. Okay, because they don't slide, we're looking at what? Static friction, because there's no sliding going on. We cannot use kinetic friction because this would only happen when they start to slide against one another. Okay, but imagine if A increases, if I pull the lower block by a large amplitude, let go, and it's going to oscillate, rapidly back and forth with a large acceleration, right? And that, in order to keep up with the lower block, the top block has to have the same acceleration, but it is only powered by static friction, which has an upper limit. Right? Static friction is the upper limit, which is μs times what? Times n, the normal force. What if there is simply not enough static friction available to provide the top block with the same acceleration as the lower block? I mean, the lower block is attached to a spring. If you pull the spring by a large amount, it's going to provide a large acceleration because the force, the restoring force, is large. Yet the top block is not direct attached to the spring. It cannot keep up with it if there's not enough static friction available. Okay, the only force that powers it horizontally is the static friction, right? So question is, what is the maximum amplitude A I can pull the lower block to, so that as I let go of the lower block, they will both move in the same simple harmonic oscillation. There is not sliding, there's no skidding going on between block 1 and 2. Well, the idea is this. Again, for the top block, the only force powering it horizontally is the static friction. So for the top block, I have Fs equals mass times acceleration of 2. Okay, and Fs is anywhere between 0 and maximum value, which is μs times n, and which is in this case μs times m2g. And this tells me that the maximum amount of A2 max is equal to μs times g. Okay, you should be familiar with this from physics 8a. Any object that is powered only by static friction, there is a maximum amount of acceleration that's available to it, and that is μs times g if it moves horizontally, with normal force being equal to its own weight. Okay, remember in 8a we talked about the car, right, being accelerated on a horizontal road. Here's the maximum acceleration available to the car, μs times g. It's the same thing. On the other hand, for both blocks to move together in a simple harmonic oscillation, I can find the acceleration of that. So acceleration for both blocks. In order to find that acceleration, apply Newton's second law. So I have the only external force exerted on both blocks as one system, that is negative kx. Okay, I can no longer, there's no force between object 1 and 2 in this context, because I'm thinking of object 1 and 2 as a single system. So the force between them, the static friction, is an internal force, which I don't consider. Negative kx is the only horizontal external force. And that equals total mass times acceleration. Mass is m1 plus m2, because I'm thinking of both objects as one system, A. Okay? And naturally, that leads to a solution. So that leads to a solution of simple harmonic oscillation. I know what x equals A cosine, omega t plus phi initial. In this case, actually phi initial equals 0. If I pull it all the way to the end, I start with a maximum amplitude of oscillation, so phi initial equals 0, but doesn't really matter. See, my job is to find the acceleration from this last expression and compare with the maximum acceleration A2 can possibly sustain. Okay, in order for them to keep together, the acceleration provided by the simple harmonic oscillation cannot exceed what A2, what object 2 is capable of achieving from static friction. So from the last expression, I can take a derivative, I can find V. I take another derivative, I can find A. So V equals dx dt, okay? And you do that, it's negative omega A sine omega t plus phi initial. And then you take one more derivative, you get A equals to what? dv dt. And we all know what that is. That equals negative omega squared A, again, cosine omega t plus phi initial. Okay, given this last expression for the acceleration, can we find the maximum value? Okay, I want to make sure the maximum value of this acceleration does not exceed the maximum possible value of A2, which is mu s times g. So I get A max in a simple harmonic oscillation its magnitude is omega squared times A, isn't it? Okay, because cosine theta cannot possibly exceed 1. I mean, forget about negative sign, I'm just looking at the magnitude here. And so that's maximum. Now, in order not to slip, no slipping between the two, that means that A max must be lower than A2 max. This A2 max is whatever, I don't care what happens, whatever happens to, to the rest of the system, object 2 is only powered by static friction. So no matter what happens, it can only come up with as much as mu s times g, that is maximum acceleration A2. In order to participate in this simple harmonic oscillation without any slipping, you want to make sure that the maximum acceleration experienced by A2, by object 2, during the entire simple harmonic oscillation be less than what it came capable to accelerate, which is A2 max. So I can be equal to just marginally, okay? So that tells me that omega squared A must be equal or less than mu s g, okay? That gives me A max. If you look at the equal sign, mu s g over omega squared. Now I know what omega is. Omega is the square root of k over the total mass, m1 plus m2. Okay, so this is mu s over omega squared, so that would be m1 plus m2 over k. That is the maximum amplitude of oscillation the simple harmonic system can have in order to prevent slipping from happening. Okay, so that's the second discussion problem.